Hi boys and girls. This video comprises the lecture for section 9.9 entitled Geometric Power Series, and it starts on page 669 if you want to follow along. You know I always think that's a great idea. In this section and the next you will study several techniques for finding a power series that represents a given function. And we're going to specifically talk about a power series that has a geometric form. Now remember what the geometric series looks like. We have some term that looks like a times r to the n power. We know that r, the ratio, if the absolute value of r is less than 1, we have a convergent series. And you know the rest of it, but we want to keep our series convergent, so basically we'll focus on this for now. But the other thing that we found was that the sum of a convergent geometric series is a over 1 minus r. So when you have a geometric series and you know what a is and you know what r is, you can actually say what the sum of that series is. So what we're going to look at is a function that looks very much like a geometric series, or at least the sum of a geometric series. This function right here. 1 over, let me change colors for a second here, since I'm moving into the green font. 1 over 1 minus x. Now look how similar this is to a over 1 minus r. If we say that a is equal to 1 and r is equal to x, then we can call this function a geometric series, or this would be the sum of a geometric series, right? Now the general term then, because we have a equals 1 and r equals x, the general term of this function would look like this. You would have 1, which is a, and then since r is x, it would be x to the n. And when you start generating some of those terms, you would get, when n is equal to 0, you get 1. This is from n equals 0 to infinity. Plus x squared, plus x cubed. Good grief, this has got to be one of the easiest power series to generate ever, right? And remember that this series, we can keep it convergent since our radius is x when the absolute value of x is less than 1. So remember that ordinarily when we were looking at geometric series, there was a number in there for r. Like maybe we had something like 2 times 1/3 to the n power, and we were identifying 1/3 and saying, ah, that's less than 1, therefore that series converges. But now we have a variable as our r, so we could make this a divergent series if we wanted to. We could say, hey, let x be 4. If this was 4 to the n, divergent series. But since we're going to keep it less than 1, we could say let x be 1/2. That would be a convergent series. As long as the x value that is sitting here, if the absolute value of that is less than 1, this series will converge. And the sum will be 1 over x minus 1. So if we did let this x be 1/2, the sum of this series would be 1 over 1/2 minus 1, which would end up being -2. So that's how it works when you have a variable there. You have a series that has the potential to be convergent or divergent, and using the rules of the series, in this case a geometric series, we will keep it convergent as long as this x value is less than 1, and this would therefore be the sum. So that is sort of this setup. We revisited, I guess I could have just pointed to these things. I forgot that these were the things I had here. But essentially, that's what the geometric series looks like, the sum, the interval of convergence, and then when we let a equal 1, r equals x for the function that we were looking at, centered at 0 here, notice that. This is the series, and we can keep it convergent by letting the absolute value of x stay less than 1. Kind of cool. Now the thing about this function, though, is that this series, since our interval of convergence was when x, the absolute value of x, was less than 1, that kept us between -1 and 1, right? So our interval of convergence was -1, 1. And that series representing that function was only convergent on that interval. But look at the actual function 1 over 1 minus x. That's this guy right here. It's actually defined everywhere except for where the vertical asymptote is at 1. So yet our series, which we have defined using this function, is only defined on the interval from -1 to +1. That's our interval of convergence. So this little dotted line here represents the interval of convergence for the series. We may, however, want to represent this same kind of function in another interval. To do so, we must develop another series. We could say, well, what if I want to center this same kind of series at -1? Well, what we're going to do is take our 1 over 1 minus x, and we're going to make this equivalent to a form of that same fraction here, this same rational expression, but one in which we have x plus 1 as this term, right? Because if x plus 1 is this term, I have a series centered at -1. But if I'm going to do that, and remember I would need something minus this, I wonder what that something would be to make this true. Now you could actually set up an algebraic equation if you wanted to, but remember, this has to equal 1 minus x. So you can probably figure out if I have to have now minus the quantity x plus 1, since I'm now centered at -1, this little fellow right here is going to have to be a 2. Because think about it, when you test this out, distributing the negative here would give you minus x minus 1, and of course 2 minus x minus 1 is 1 minus x. You've got to configure it so that it's equal to 1 minus x. So you're kind of making modifications to make this work. Now the next thing that you have to do is you can't have 2 minus your radius quantity. It has to be 1 minus your radius quantity. So the way we're going to turn this 2 back into a 1 is we're going to divide every term in this rational expression by 2. Notice now, in a dramatic change of color, that my numerator is 1/2. I have 1 minus, and now this becomes x plus 1 over 2. Now, boys and girls, this is in the form a over 1 minus r. We had to work it. We had to make it happen because once we had to have our function centered at -1, we had to put this x plus 1 quantity in, but in doing so, we had to sort of arrange and configure things to get it to look like this again, and this is what we ended up with. So for this series that we have centered at -1, a is 1/2. And our radius is x plus 1 over 2. Okay, so with that in mind, notice what our general term looks like. 1/2 is the a, and then of course x plus 1 over 2 to the n power is the general term. Once you identify the a and the radius, you know how to set up the general term. Now, let's keep this convergent. Remember, if this is my radius, to keep it convergent, the absolute value of this has to be less than 1. Now we can multiply both sides by 2 because the absolute value of 2 is 2, so this becomes absolute value of x plus 1 has to be less than 2, which is what I have written here. Now, that means your radius of convergence is 2, and your interval of convergence, since we're centered at -1, plus 2, minus 2 on either side, your interval of convergence will be -3, 1. So now let's do this. I was just showing you on this example how all this happened. Let's make it happen for one that we don't already see the answer to. Let's find a power series for 4 over x plus 2 centered at 0. Notice it doesn't say the word geometric anywhere, but this looks a lot like our old friend 1 over 1 minus x. I bet I can make this happen. The first thing I'm going to do is, so he's just watching to see if you're going to be able to make this work. I'm going to write this as 4 over 2 plus x. And then I'm going to say, I don't want that to be a 2. I want that to be a 1. Let's divide everything in the problem by 2 because I need that constant to be a 1. This becomes now 2 over 1 plus x over 2. Gosh, I'm so close. If only this were a minus. Well, I can easily rewrite it and make that happen by saying 1 minus a negative x over 2. Now, boys and girls, Does this look like our old familiar friend a over 1 minus r? Why, it sure does. A is 2. R is negative x over 2. If we were putting our general term together, we would say n equals 0 to infinity probably, and our a would be 2. We would put negative x over 2 to the n power. Now, I do want to make a little modification here. Since there's a negative in here, we should probably separate that out and recognize it means that it's going to be an alternating series. So I can rewrite this as 2 and then write this as negative 1 to the n, and then I've got x over 2 to the n as my general term. Now, you're probably wondering, wait a minute, I wonder what the interval of convergence is. I'm glad you asked, boys and girls. We know that we need to keep the radius, which is the absolute value of negative x over 2 less than 1. Of course, the absolute value of x is just the negative x is just the absolute value of x. And if I multiply by that 2, I get less than 2. So the radius of convergence is 2. The interval of convergence will be negative 2 and 2. Great job, boys and girls. We're going to do one more of these, and this time it's going to be centered at 1. So we're going to take this guy, which doesn't really look a whole lot like our a over 1 minus r yet, but we are definitely going to make that happen. Let's remember that we're kind of needing to get it to look like this form, something like that. It doesn't necessarily have to be 1. The numerator, we'll see what happens. Okay, so let's see if we can make this happen. First of all, I know that I need this to be, since it's centered at 1, I need to be x minus 1. So what I can do is just add 1 over here, right? 1 plus x minus 1 is x. So I've got 1 plus x minus 1. I kind of, just finagled that and made it happen. Now, it's not quite right, though, because I need a 1 minus the radius quantity. So let's rewrite this again, going 1 minus a negative, I should probably put a square bracket here, x minus 1. Okay, so that minus a negative takes care of the fact that it was actually plus, but now I have it arranged so that I can identify the a, which is 1, and the r, which is, I'm going to keep it like this right now, negative x minus 1. That's the quantity. So what will our general term look like? N equals 0 to infinity of a, which is 1, so I don't need to write that. And then I have this quantity, x minus 1, to the n. But do you recognize that once again, we should separate out that negative because that's just the alternating piece. That makes negative 1 to the n, and then x minus 1 to the n. There's our general term. You could generate a few terms if you wanted to, just to be fancy, but for now I'm just going to focus on now finding the radius of convergence. We're going to take the absolute value of negative x minus 1, knowing that we need to keep this less than 1. Now remember, we keep this intact because since our series is centered at 1, this is the term that we're determining the radius of convergence on. Obviously, since that negative is inside the absolute value bars, essentially this is what we're looking at. Our radius of convergence therefore is 1, and since we're centered at 1, adding 1 and subtracting 1 from this puts us at an interval of 0, 2. Now on this next slide, I just want to generally discuss the fact that we can do operations with power series. Power series are very versatile, and the following list demonstrates operations which can be performed on them. These operations, used with differentiation and integration, provide a means of developing power series for a variety of elementary functions. So notice that if we start with f of x being this power series and g of x being this power series, f of kx would mean when we take our a sub n term, we would rewrite it a sub n, and then this would be kx to the n, which would actually be a sub n, k to the n, x to the n. So putting that constant in there in front of the x term just rearranges the general term in that way, and that should be kind of logical. What if we put x to the n in for x in the general term? We would have a sub n, and then our general term is x to the n, but let's replace that with x to the big N to the n. That would simplify to a to the n, x to the big N, or n big N, they write it that way. Of course, since this is power to a power, you would multiply those exponents. And then if you added your two series together, it would just be adding it term by term, adding or subtracting term by term. These operations can change the interval of convergence for the resulting series. So once the new series is formed, it is necessary to determine, the new interval of convergence. Now, say the interval of convergence for this is 0, 2, maybe this is 1, 3. Your new series, if you added them or did any of these weird little things, you'd have to check again. It's not necessarily going to be either of the original intervals of convergence. Now, boys and girls, in a surprise move, I'm going to add on section 910 here and get this puppy out of the way. Taylor and MacLaurin series, and this is page 676. In this section, we will study a general procedure for deriving the power series for a function that has derivatives of all orders. That means derivative first, second, third, fourth, on and on and on and on. The following theorem gives the form that every convergent power series must take. Notice we've got blah, 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 but the resultant series looks like this. This should look very familiar. F of c, f prime of c times x minus c, f double prime of c over 2 factorial x minus c quantity squared. Here's your general term, the nth derivative at c over n factorial x minus c to the n, and etc., etc., etc. Note that the coefficients of the power series in the above theorem are precisely the coefficients of the Taylor polynomials for f of x at c as defined in section 9.7. For this reason, the series is called the Taylor series for f of x at c. Now, back in 9.7, when we were developing these polynomial approximations, they were finite series. Maybe we had p sub 4, where we were supposed to take it out to the fourth derivative. But now we are expanding that idea to infinity. And in doing so, we have an infinite series now, which is called a Taylor series. The difference between the series and the polynomials, these polynomials are approximation polynomials that are finite, whereas the Taylor series, of course, is an infinite series. Now, we have our definitions of a Taylor and MacLaurin series. This should be familiar. Same deal. This is called the Taylor series, and if c is equal to 0, then it's the MacLaurin series. If you know the pattern for the coefficients of the Taylor polynomials for a function, you can extend the pattern easily to form the corresponding Taylor series. For instance, the following fourth Taylor polynomial for natural log of x, fourth taking you out to the fourth degree derivative, that looks like that. But from this pattern, you can obtain the Taylor series for natural log of x. Doesn't look much different, except that, of course, we don't stop. We do plus dot dot dot, because, of course, it continues on to infinity. Notice we also develop a general term by looking at the pattern of the terms in the series and then generating that general term for the series. Now, let's form a power series here for sine x, and we're going to make it the MacLaurin series, which means, of course, c is 0, so we've got f of 0 plus f prime of 0, etc., etc., etc. Now, I went ahead and just took a screenshot of all of the work from the book so that we don't have to do this. And so our series is going to look like this. We're going to have f of 0, which is 0, and then plus 1 times x, which is x, and then plus 0 times x squared. Hold on one second. Before I get lost in all of the 0 terms that are about to happen, let me identify what I have here in the setup. These terms, this one, nope, this one, and this one, for the original function value, the second derivative, and the fourth derivative are zeros. So notice that those terms are not going to show up in your resulting polynomial. So I was going to write them out with the zeros, but since I started getting confused, let's not do that. F of 0 is 0, so we're not going to have a term there. Let's start with the coefficient 1, which goes with the x term, x. Next, we're not going to have the second degree term because that coefficient is 0. Let's go right to this one, which is minus, this is going to be 1 times x cubed over 3 factorial. Now we would ordinarily go to the fourth term, but again that coefficient is 0, so let's go to the fifth term, which is a positive 1, that's the coefficient, x to the fifth over 5 factorial. Notice the terms are alternating, so it's going to be minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, etc. That is a power series, the MacLaurin power series for sine of x. Now let's also determine the interval of convergence. We're going to use the ratio test to do this. Remember back in the day when we did this, the nth term for this, actually let me pause and let me write this down. Okay, boys and girls, this is the nth term. I just went ahead and went off of my live recording to write it down. Remember how we discover if a series converges. We are going to take the absolute value of the n plus 1 term, a sub n plus 1 over a sub n, the limit as n approaches infinity. That's the ratio test. Remember, our limit less than 0 means that it converges. So that's what we're looking for. I'm sorry, less than 1. Sorry, less than 1, it converges. So we're going to do the ratio test here, but remember I'm going to be using the absolute value of these terms. So when I do take the absolute value of this term, this negative 1 to the n piece, which is the alternating piece, is again sort of pointless here because it's the absolute value. So let me go ahead and put in the n plus 1 term. This will be 2n plus 1 plus 1, and that's going to be 2n plus 2 plus 1, which is 2n plus 3. And then if I put the 2, again, n plus 1 in here, 2n plus 1, 2 plus 1 is 2n plus 3. And now let me go ahead and take this limit. Limit as n approaches infinity. I'm going to do the shortcut where I write the n plus 1 term times the reciprocal of the n term. And so this is going to be, remember this is going to be x to the 2n plus 3, but I'm going to write it this way. X to the 2n plus 1 times x squared. Isn't it true that when you add 2n plus 1 plus 2, you get 2n plus 3? Now same thing for the factorials. This is now 2n plus 3 factorial, but I'm going to write it as 2n plus 3, 2n plus 2, and then 2n plus 1 factorial. Why am I doing that? Because I want this guy and this guy to cancel as I now multiply the reciprocal of the original a sub n term. This 2n plus 1 factorial here, and then of course x to the 2n plus 1 here, give me these opportunities to cancel. Love it. This means that I am now at the limit as n approaches infinity of x squared over 2n plus 3, 2n plus 2, and now the moment of truth, boys and girls. It's time to plug infinity into this denominator and determine what happens. Now, oops, that's an x squared, isn't it? Now remember that x could be a number. Ordinarily this limit would be some sort of number, 2, 4, 7. It doesn't matter what x is. Because the denominator is a big fat infinity, no matter what you put in for x, you're going to get a limit of 0, which is less than 1. So we don't have to say, you know what, I need to keep x less than 4 for this to work, or x greater than this. No, because it's sitting on top of a big fat infinity, x can be negative 4,000, positive 2 million, doesn't matter. The limit is 0, that's less than 1, which tells you this series converges everywhere. The radius of convergence is infinity, and the interval of convergence is this. Okay, we're almost done, boys and girls. Now we're going to look at guidelines for finding a Taylor series, differentiate f of x several times, first, second, third, fourth derivative, evaluate its c, Try to recognize a pattern. This is so that you can come up with the nth general term. Use a sequence developed in the first step to form the Taylor coefficients. Bam, bam, bam. Then within this interval of convergence, determine whether or not the series converges. So there you have it. The direct determination of Taylor or MacLaurin coefficients using successive differentiation can be difficult, and the next example illustrates a shortcut. Don't we all love shortcuts? For finding the coefficients indirectly using the coefficients of a known Taylor or MacLaurin series. Find the MacLaurin series for sine x squared. All right, what is the first derivative? Already we're getting a little worried because we can see this is going to be 2x cosine x. Then it's product rule, something that we don't really want to deal with. But here's what we can do. We can say the series for sine x is equal to, we just developed this, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. And so say, you know what? Sine x squared is x squared minus x squared cubed, x to the 6th over 3 factorial, plus x squared to the 5th, x to the 10th over 5 factorial, minus x squared to the 7th, x to the 14th over 7 factorial, etc. Bada bing, boys and girls, that's how that works. Now, with that in mind, notice that deriving Taylor series from a basic list is often a good idea. The following list provides the power series for several elementary functions with the corresponding intervals of convergence. A few of these should be memorized. For sure, this one, this one, this one, and this one. And you should memorize the general term of each of these, and definitely also the intervals of convergence. And but notice there's patterns. Notice that sine x and cosine x have exactly the opposite terms, right? This has the odd terms, this has the even terms, and so that one's not hard. E to the x is not hard either. It's x squared over 2. Everything's positive. The coefficients are all 1 over the factorials. That's a really easy one. Natural log, maybe not quite as easy. Actually, you should do natural log. Oh, this is natural log of x, sorry. These are secondarily important, I suppose. These, nah, wouldn't worry too much about those. So, there you have it. Let's do our last example where we're going to find the power series for cosine square root of x using the known power series for cosine. Cosine of x is, I believe it is, let me see if I can remember what it is. Give me 1 second. I'm actually just going to find it here. It's coming. Here we go. The power series for cosine is 1. See, I should memorize them too. Minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Once you get started, you kind of know it, which means cosine of square root of x, 1 minus square root of x squared is x over 2 factorial. The square root of x to the 4th power is x squared over 4 factorial. And then the square root of x to the 6th is x cubed over 6 factorial plus dot, dot, dot. This should also be plus dot, dot, dot. And that's the end of this lecture, boys and girls. Math is the language God used to write the universe. That's what Galileo says. I believe it. This beautiful picture from the Hubble telescope seems to confirm that statement. Your homework, I've got 4 problems from section 9 and 5 problems from section 9-10 for you to practice. God bless you, boys and girls.